this thing we call implicit differentiation. You see, what we have been doing is explicit differentiation, although we very rarely call it that. We say, oh, it's differentiation. So what's implicit differentiation? It's exactly what we've been looking at. Rates of change, the chain rule, call it whatever you like, it's all the same thing. So y equals x squared. So there's a lot of working going on in the background when we differentiate it. Now in reality we just write this down and go, oh, y dx is 2x. But what we're really doing is differentiating both sides with respect to x. Now on the left hand side, I can't differentiate y with respect to x. It's the wrong pronumeral. But I can do it with respect to y. But I can't just change the question. So I multiply it by dy dx to balance it out. So I end up with 1 times dy dx is 2x. And so that's how we get our answer that we normally just write down. Dy dx is 2x. So whilst we have been differentiating explicitly and just getting the answer straight away, we actually have been doing implicit differentiation without actually knowing it. Now it means we can differentiate something like this. I don't have to make y the subject. I can say, well, I want to still differentiate with respect to x. So if I differentiate x with respect to x, I'll get 1. But when I differentiate y squared, I can't do that with respect to x, so I'll differentiate it with respect to y and times by dy dx to balance it back out. So I end up with 1 is equal to 2y times dy dx. Make dy dx the subject and I now have a formula. So the difference with this curve is instead of substituting in an x value to find the slope of the tangent, I substitute in a y value. Now why? Well, if you think about the curve, this is a parabola on its side. If I was to substitute in an x value and find the derivative, well, there's 2 possible answers, because I get 2 points for that x value, and they would produce different tangents with different slopes, because it's not a function. But if I'm substituting in a y value, so let's say there's only 1 point it goes to. So then I get a definite answer. If I had to differentiate something like this with respect to x squared y cubed, I've got 2 things. Product rule. I still use the product rule. I just got to be careful. Write down the first, x squared. Diff the second. Well, hang on, the second is y cubed. I can't differentiate that with respect to x, so I'll differentiate it with respect to y, 3y squared, but then I'll multiply it by dy dx to balance it out. So the differentiating the seconds becomes 3y squared dy dx, plus, write down the second, y cubed, diff the first, that's fine, I can do that one, 2x, and so that would be my derivative. A question like this. I want to find the equation of a tangent to a circle at the point 1, 2 root 2. Okay. X squared plus y squared is equal to 9. Differentiate. X squared, not a problem, that's 2x. Y squared, oh hang on, I can't differentiate that with respect to x, but I can do it with respect to y. So I'll do that. 2y, but to balance it out, I'll multiply by dy dx. That will equal, differentiate 9, you get 0. 2y dy dx is minus 2x, moving it to the other side, and I end up with this expression. Dy dx is equal to minus x over y. So for this one, I have to substitute in both an x value and a y value. Think of the curve. If you've got a circle, if I substitute in an x value, 2 possible points, no good. If I substitute in a y value, 2 possible points, no good. But if I substitute in an x and a y value, now I've narrowed it down to 1 specific point, and I can do the question. So at the point 1, 2 root 2, dy dx is minus 1 on 2 root 2. There's my slope, point slope formula, and let's play around with that. And there it is in general form. I've got the equation of a tangent at that particular point. So that's the advantage, I guess, of using implicit differentiation. If I wanted to do it explicitly, then I would have to make, say, y the subject, and I'd get y equals plus or minus the square root of 9 minus x squared. I'd have to make a decision, which one of those am I going to go and differentiate? For this one, it'd be the positive square root. And then I'd have to differentiate 9 minus x squared to the power of a half. Go from there. Implicit differentiation allows me to do it a lot quicker. Have a go. Look,